Okay. Okay, thank you so much. Well, welcome. Thank you for being all here, listening to my talk. I hope you find it interesting and that we can all share interesting comments and ideas on this point. So, as Jonah has said, the title of the talk is An Alternative Approach to Conceptual Structuralism. We are going to approach this idea of conceptual structuralism, which is a framework, a philosophy for understanding mathematics that Solomon Feferman posed. And we are going to see how this framework relates to the well-known continuum problem posed by Cantor in the 19th century, and we are also going to approach it from an alternative view, from another point of view that maybe both Feferman and his critics have not explored that much. Okay, so that all of you are more or less know what we are talking about, we are going to start by explaining well what the continuum problem is. So you all, maybe some of you remember from the high school or or maybe in the university that we have in mathematics different sets of numbers. We have the set of the natural numbers, which is the numbers we can count with, 1, 2, 3. Some people include 0, some people don't include 0. It's much more, let's say, canonical in set theory to include 0, but well. And then we have the continuum, the set of the real numbers, which includes all the numbers in the real line. It includes all the continuum of points in the real line. Cantor was able to show, with a really revolutionary technique for understanding cardinalities, that there was no way to define a bijective function, a one-to-one map, between these two sets. So we can say that the continuum is strictly bigger, is larger in terms of cardinality than the natural number set. Okay, so this is what we can understand as this the relation, that the natural number set, which is Aleph 0 in the set theoretical notation, is smaller in terms of cardinality than the set of the real numbers, the continuum. Okay, and then he made this conjecture, which lead a little bit naturally from the other ones. He conjectured that there is no strict third intermediate set. So there is not third set, which is bigger, strictly bigger than the natural numbers and strictly smaller in terms of cardinality than the real numbers. We could write this set statement how like this. There is not, let's call it A, such that cardinality of N is smaller than cardinality of A, smaller than cardinality of R. Okay. But
can I add one question on notation?
Yeah.
What's the symbol, 2 dots and equal?
That's a definition. So, okay, so I define this cardinal, I define it as the cardinal of the natural numbers, and this I define it as C, I define it as the cardinal of the real numbers. This is the...
Okay, so the C is not equal to...
Sorry, what?
So, okay.
C.
So, Aleph 0 is not equal to C.
No, Aleph 0 is smaller than C.
Yeah,
okay.
Yeah,
so it's like, maybe, I don't know if it's the better call, but yeah, it's a annotation, yeah. Point equal is like for definition, like defining introduction and notation. Okay, so this statement seems really innocent. I mean, it's like a mathematical statement like any other in the world, but it showed up to be much intricate that we could think at the first time. And in the beginning of the 20th century, a lot of efforts in logic led to the development of a framework for understanding set theory, a framework called CF, which means Zermelo, Frenkel, which are a set of axioms, a family of axioms that are strong enough so that all the mathematics that had been done previously to that development, we could say that can be carried out through these axioms. Just in terms of these axioms, you can define all the mathematical tools that before the time of Cantor had been used. And what happened? That Gödel and Koellner in 1938 and 1963 proved that this statement, the statement of the continuum hypothesis, cannot be decided, cannot be proved, neither refuted, using the axioms of set theory. So it's yes, of course. Anytime you want to can so.
I'm reading there that Cantor conjectured that there was no third. Blah, blah.
Yeah.
And I'm reading there that there is.
Well, this is
so
the
what's the hypothesis?
well
that
the
there is or that there isn't. Right?
well.
You know, what's the exactly continuum?
Well, I think the hypothesis is strictly, well, you can ask whatever. If you are asking one, you are also asking the opposite one, because I think the hypothesis strictly is that there is not third set. Okay, Cantor was, yeah, the hypothesis says that there is no third set. In case it is false, then there would be a set. Most set theorists nowadays probably lead to thinking that it is false, but well, that's another point. But yes, it's a good remark, yeah. Okay, so we arrived to this point. It's apparently well-defined mathematical conjecture, but we see that it cannot be decided with the tools that mathematicians used to utilize in their real life. Okay, so there are a lot of this has led to a lot of discussion, a lot of controversy, and there is a group of mathematicians, there are some mathematicians that have doubted, because of this reason, whether this is an effectively meaningful and essentially definite mathematical statement. And one of these important proponents of this perspective is Solomon Feferman. Solomon Feferman has presented a philosophical framework for understanding mathematicians. He was a really eminent character in logic and in the development of a lot of important tools in mathematics and mathematics. And he has also developed a mathematical philosophical framework called Conceptual Structuralism. And according to him, in this framework, CH ends up being an intrinsically vague and undefinite statement. Okay? So we are going to see how to approach this problem. I am going to divide the talk in more or less 3 areas. The first one, I am going to try to explain you what is conceptual structuralism and which criticism it has received. After that, I am going to tell you how I would try to understand Feferman's argument so that we could be a little bit more generous with conceptual structuralism. And in the end, I would give you a more general framework to try to understand this controversy. Okay? Okay. So the idea of conceptual structuralism is to try to understand mathematics in a more connected to practice, down-to-earth way. So maybe you know that in the beginning of the 20th century there were movements in philosophy of mathematics and in logic, like intuitionism, that try to emphasize that many of the tools that mathematicians used in many occasions, such as the excluded middle or arbitrary sets, etc., were separated from human intuition, from our real-life understanding. Feferman somewhat tries to go in the same direction. He's also really, he also leans a little bit towards predicativism. So we are going to try to see what his ideas are. The main idea of conceptual structuralism is that mathematical notions consist on structures that must be defined, must be that we can understand through real life easy experiences such as counting, ordering, joining, etc. So, for example, in real life, you can start to take collections of things. You can start to add up collections. You can follow your counts, and you can still you can count indefinitely. So these external processes lead us, for example, to a pre-theoretical notion of the natural numbers. It could be, and then using this notion, we can maybe arrive to a little bit more complicated notions. But according to Feferman, we cannot go really far in that direction. He characterized this idea, this philosophical framework, around 10 theses. These 10 theses can be considered somewhat concise, somewhat obscure in some moments. I am going to put them here so you can see it. And if we follow this, according to Feferman, statements like CH are not completely clear. So they are not completely clear, else they do not have a definite truth value. Okay. Let's see. This is the thesis. I am going to. Yeah?
Feferman? Is that the Feferman from Feferman wrote and the
Theorem? Yeah, it's the same one. Yeah.
Is he still alive? Or no?
No, he died in 2016, I think. Yeah, like.
Of course, yeah, 6 years. Huh?
6 years? I thought it was 10 years ago.
Oh, 10 years ago?
Maybe 10 years ago. He
Yeah.
died like 16 or something.
Yeah, I think 16,
We were in
yes.
Stanford.
Huh?
We were in Stanford, I think, or a little bit later. A little bit later, 16, I think.
And in that
No, I saw him in Stanford, maybe. Well, anyway.
Well,
yeah.
yes, I think it was 16. So these are like the last, like his last ideas in, like his last philosophical ideas. This is all of this is 2011, 2013, more or less that time. Okay, so take a look at the thesis. You don't need to memorize it, but let's try to follow them. So the first one says, the basic objects of mathematical thought exist only as mental conceptions. Though the source of these conceptions lies in everyday experience in manifold ways, in the processes of counting, ordering, matching, combining, separating, and locating in space and time. Theoretical mathematics has its source in the recognition that these processes are independent of the materials or objects to which they are applied, and they are potentially endlessly repeatable. Okay, so this idea that these processes are endlessly repeatable and that they are independent of the object, of the token, let me put it that way, that we are using in every case, lead us to a pre-theoretical or a theoretical conception of, for example, the natural numbers. Okay? Okay, this one is the one I like the most, and it's the one, maybe the one I think has flight a little bit under the radar of many authors. The basic conception of mathematics are of certain kinds of relatively simple ideal world pictures, which are not objects in isolation, but of structures, i.e., coherently conceived groups of objects interconnected by by few simple relations and operations. They are communicated and understood prior to any axiomatics, indeed prior to any systematic logical development. Okay, so this is the point. Well, he then gives his idea of a structure, mathematical structure. I am not going to deep dive into structuralism today. If you want to ask something later, you can. But the interesting point is these ideal world pictures. It's a little bit also hidden because of that hyphen, but here he's saying something like, well, mathematical objects have to be world pictures. I mean, they have to help us model and shape the world we live in. So these objects need to have a relation with the world we live in. They cannot be theoretical, freestanding notions that nobody knows why we got them for. Okay, this is the idea. But later I am going to tell you why I think this has flown a little bit under the radar. Okay, some significant feature of this structure are elicited directly from the word pictures we described, while other features might be less certain. Mathematics needs little to get started, and once started, a little bit goes a long way. Okay, so here he's more or less saying that with really few, really small theoretical assumptions, for example, just as the natural number structure, you can define a huge amount of theoretical work and a huge amount of tools that are useful for science, for mathematics, for every application that you need. In fact, most of what is actually done in mathematics, even if we have complex numbers, if we have functional analysis, if we have abstract algebra, topology, I don't know what, almost everything can be carried through in a relatively simple structure like this. So this is more or less that idea that Feferman tries to represent when he says that of a little bit goes a long way. Okay, and the fifth one is... Yeah?
Can you progress? Before, does he precise what is the...
I am... Okay.
Here. It's the same basic conception. Does he precise what he means by basic conception?
What do you mean here?
No, at the beginning of 3, sorry.
Okay.
The basic conceptions.
The basic conception of mathematics? Well, yeah, he does not make precise anything. This is another point that I want to. In fact, in the text of 2011, after giving all the theses, he says something like, "There will be time to develop more these theses," or something like that. Or he says something like, "But I don't have space now for that." So I mean, he is not clear with. That's another point that I want to emphasize. He's not clear with what exactly those things mean. He doesn't develop these theses with a lot of precision in the end. So this is one of the reasons why this needs a little bit of an extra interpretation. Okay, but we can in this topic there is also we can relate to the idea of unfolding of Feferman. Feferman developed like a theoretical construction, a theoretical tool, which is the unfolding of a determinate set of symbols. So you can start like with really few operations with basic objects such as the natural numbers, the basic succession operation, and he asks like the question of which are the most the minimal theoretical tools, the minimal language that we need to assume so that all this stuff makes sense, and this creates like an unfolding. He calls it unfolding of a certain theory. So it's a theoretical detail, and I think that this idea of basic conceptions that then develop a little bit more into a more sophisticated theoretical framework is related to the concept of unfolding. But unfortunately, Feferman doesn't make it so explicit. Okay?
But also the structure, right? So
Yeah, exactly.
Exactly. So, but the idea is he's defending the structuralism, so the minimal, the basic
Yes.
working tool is a structure, it's not an object, it's not a property.
Yeah, that's another point.
It's
Yeah.
not a mental construction, it's a structure. So that's a little bit, I think, the idea. Facing against Platonist or formalist or whatever. I think.
One follow-up.
Yes.
And, yeah, because I was going to ask you, you were pointing that, and that's the set of natural numbers.
Yeah.
But you call it a structure to that.
Well,
This is structure, this
yes.
is structure you're pointing there.
Okay. Yes.
Is that a structure, or is it just a set?
Yes,
Or
but
it's
I agree with. I agree. I mean, well, we mathematicians tend to simplify a little bit sometimes, and tend to omit signs when they are like followable from the context. So in reality, when I write the natural numbers, I would be writing something like the natural numbers with a 0 and the successor operation or something like that. Okay, so.
Okay, yeah. So here in his axiom, structures is like mathematical structure, set and stuff.
Probably, so I didn't ask Feferman, but I think that it's most coherent with what he says to understand, yes, basic conception of mathematical structures, yes. Okay?
Sorry. Basic conception and structure are the same?
Yes, so, which are not the, yes, so the basic conceptions have to be structures. Okay. Okay, but relatively simple structures, such as the natural number with the operation, etc. Okay. Okay. Yes, feel free to ask anything, because then the talk is going to be a little bit smoother and better for everyone. Okay, and this, the number 5, is where he tries to argue against continuum hypothesis. He says something like that: basic conceptions differ in the degree of clarity. Okay, as you can ask me what is exactly a degree of clarity. Well, I don't really know what you can understand by that. But well, one can speak of what is true in a given conception, but the notion of truth might only be partial. Truth in full is applicable only to completely clear conceptions. Okay, so this is where the argument against continuum hypothesis comes from. It should be something like you can define a continuum hypothesis in determining conceptions. In fact, this hypothesis, in order to be defined, has to live in third-order arithmetic. So we can talk of first-order arithmetic, where we can quantify over natural numbers. We could also talk on second-order arithmetic, where we can quantify on sets of natural numbers, but a set of a natural number is a real number, so we can, with that, make easier analysis and that. And in order to make sense of continuum hypothesis, we have to quantify on, this is a subset of R, so we have to quantify on sets of real numbers, we have sets of natural numbers. So in that case, I want to write it, I don't know, with an X hat, we would need to quantify on these sets of natural numbers. So continuum hypothesis lives in third-order arithmetic in the end. So Feferman would point out to the idea that third-order arithmetic is a not clear conception, it's an unclear conception, so that there is no full truth conditions to be expected from that conception. Okay, but then he says, what is clear in a given conception is time dependent, both for the individual and historically. So he's saying that it is absolutely subjective whether a conception is clear or not. So he's making there, like, he's like falling, he's giving problems to his own argument. Then he says, pure theoretical mathematics is a body of thought. Well, the later ones, I am not going to enter a lot of them because they are not so interesting for the argument that we are going to develop. For me, the most interesting ones are the third one, the 5th one, and the 6th one, because he tries, maybe undermines a little bit his own argument. He then develops some ideas around succession, collection, etc. I'm not going to spend a lot of here, because then we will lack a bit of time. The general. Okay, and the 10th one is interesting also. It's not my focus on this talk, but it points out at another interesting idea of conceptual structuralism. He says that the objectivity of mathematics lies in its stability and coherence under repeated communication, critical scrutiny, and expansion by many individuals, often working independently of each other. Incoherent concepts, etc., are eventually filtered out from mathematics. the objectivity of mathematics is a special case of intersubjective objectivity that is ubiquitous in social reality. So here he's like pointing out at the idea that mathematics is kind of a convention. It's developed by a social convention. This is, of course, a really controversial point. But this is not my focus on this moment. It will be my focus later. There have been some developments of institutional theory of mathematics related to speech-act theory, for example, which are quite interesting, and we could talk about them in another occasion, but they are not my focus now, okay? Okay, so here we find where the argument against clarity of the continuum hypothesis is the thesis 5 implies that any unclear conception is not going to have a definite truth value. And according to Feferman, there is a progressive loss of clarity when stepping from structures like the natural numbers, where we can just count until the end, to something like the set theoretical continuum. I mean, in the continuum, in the geometrical continuum, it seems that it is the Euclidean geometrical continuum. It seems to be like a really intuitive structure that we can work really well with. But in mathematics, we want to define analytically all the concepts that we can. So the continuum is defined through a set of sequences. We define the continuum in terms of sets of natural numbers. Okay, so if you take a set of natural numbers, like, I don't know, C2 for the even numbers, for example, you can associate this with a decimal binary expansion of a real number. You can take as 1 the numbers which are in the set, and 0 the numbers which are not. So, oops. Okay, so we could understand real numbers as set theory in natural numbers. But for Feferman, that is going too far. That is like an unclear and not too precise conception. He also defends predicative mathematics, so he thinks that this definition does not follow up really well the conceptions of predicative mathematics. So for him there is a progressive loss of clarity, and when we arrive to this set, parts of n, which is what we need for defining continuum hypothesis, for him clarity is completely lost. Okay, but Feferman doesn't go really far with that argument, and he's like subject to a lot of criticism. And one of the strongest ones has been given by Koellner, and I'm going to address it like a little bit briefly. Most of the counter-arguments that Koellner presents are a little bit meta-mathematical, so I don't want to get into the details. But well, we can see exactly what does he point at to. First one, he says that conceptual structuralism is ambiguous regarding the status of CH. I mean, it can be a good point because conceptual structuralism is really ambiguous, but he says that there is nothing in conceptual structuralism that can say anything about the status of CH. So we are going to try to address that point. After that, he also tells us that the clarity argument is unstable and problematic. Okay, we have seen that Feferman does not give a lot of details on the clarity argument. Koellner tries to understand it a little bit more precisely, and he gives a lot of meta-mathematical reasons so that we don't need exactly to follow the clarity argument. For example, One way to evaluate whether a certain structure is clearly defined, is whether it can be described univocally by a set of categorical axioms. A categorical theory determines up to isomorphism any structure. So in case a structure is defined in by a categorical set of axioms, then we can say that this theory, this set of axioms, this structure corresponding, this conception, is completely clear. But set theory is not categorical, but arithmetic neither is categorical. So in that case, we have like a symmetry between the metamathematical properties of arithmetic and of set theory. And for this reason, there is not like it is not easy to see a strong reason for saying that one of them is clear while the other not. And he develops a little bit more the argument. Now, point 3 says that there is a huge problem in thesis number 10 that I showed to you. There is a huge problem in understanding mathematics as something dependent on social conventions. So again, I'm not going to treat this point now because it's not my follow in this moment, but I could have told Koellner if I had him here, well, check all what has been developed around institutional theory of mathematics, etc. Because there can be something there, so this understanding could be consistent. We cannot reject it because without any other, without analyzing it further. Okay. Let's see. I am missing a slide. Maybe it is a little bit further. Well, I am going to do this one. Okay. Okay. So this is something. This is another point Feferman makes. So after we see all this criticism that that Koellner makes to Feferman clarity argument, we are going to see a little bit what Feferman says in the end of his text in 2011. He says, there is no problem to put oneself in the mental frame of mind of what this is what the cumulative hierarchy looks like. Okay, so the cumulative hierarchy, departing from the CF set of axioms, the most natural way to make a model of them is what is called the cumulative hierarchy, which is basically to start at the void set and start adding like subsets of previously defined sets. Okay, so with that you can construct like a huge apparatus of set theory and develop like a structure with well all these axioms make sense. Okay, and he says something like, well, of course, the cumulative hierarchy is a hugely strong mathematical conception, so for Feferman it must be absolutely unclear because it's much stronger than what is needed for defining CH. What is needed for defining CH. But he says here that there is no problem to put oneself in the mental frame of mind of this is what the cumulative hierarchy looks like, for which one can see that such and such propositions, including the axioms of CFC, are more or less obviously true. So I have thought set theory many times, and here he says, and I have presented it in terms of this ideal world picture, which with only the caveat that this is what things are supposed to be like in that world, rather than to assert that that's the way the world actually is. Okay, so what is he saying here? First, note a detail. Here he's talking about ideal world pictures. But here, in thesis 3, he's talking about ideal world picture. so that the text gets enough difficult to understand for me. World picture. Okay, so he's like trying to make a subtle difference between these two points. Yeah, so if you
just
trying to
this is a small dash.
this small dash exactly,
Okay.
and there is another text where he omits the hyphen. He just says ideal world picture. I was like 3 months reading the same text once again after I noticed that point. Okay, so I think I interpret this as he's trying to say that we can understand perfectly what the cumulative hierarchy looks like, okay? But this is an ideal world picture. This means it is a picture and a conception that we can understand, but that is separated from the world we live in. Okay? But then he's not talking in terms of clarity. I mean, he's recognizing that it is a perfectly clear conception. So how can this be? How can you how can you compatibilize saying that these conceptions and even weaker ones are completely unclear, but at the same time saying that we can perfectly put us in the mental frame of saying how they look like. I think this contradicts the most obvious definition of clarity, at least for me. So he's like making effectively, as Koellner says, a quite weak argument against the clarity of CH. It's an argument that gives us a lot of problems. Okay, but the idea of connection to the real world, I'm going to check how much time I have. Oof. Yeah. Okay, I end up. I thought I had more time. Okay. Okay. So this. For this reason, I want to look more than at clarity at another point of Feferman's argument, or of another point of this argument, which is applicability. Applicability is the idea of trying to see whether the structures needed to define CH can be actually put into relation to the world we live in. Okay? Here is another point. In terms of the most important conception of mathematics, we can see, for example, finitism, predicativism, and set theory or full set theory. A finitist would only accept like finite objects, finite graph, or formal logic. A full set theorist would accept almost all the theoretical conceptions that we can see in mathematics, while a predicativist lies somewhere in the middle. The point is, like, Feferman probably lies in the green area of predicativism, and he rejects to jump into the blue area because of lack of clarity, he says. But in the end, it is not easy in terms of clarity to argue against this jump without also arguing against this jump. So if you are in the position of a finitist, you can criticize predicativists more or less with the same arguments that a predicativist would use against full set theoretical tools. Well, I am not going to, if you want, later you can ask me a little bit more. So the applicability argument lies more, resembles a little bit to the Quine and Putnam indispensability argument. But Quine and Putnam's focus is epistemological, while Feferman is more pragmatic. Feferman sometimes says something like, well, with which theoretical tools can science be developed? And with that in mind, then this is an argument for the legitimation of that theoretical tools. And in the end, we can see that we need really few mathematical tools to develop all the science we actually do in physics. So, third order arithmetic, which is the level of complexity required to define CH, is not legitimized this way. So there could be another argument given, an argument related to applications on real-life physics against something related to the legitimacy of CH. But this argument also has its limitation. It's more a negative than a positive argument. In fact, Feferman does not use it as a positive argument. And if we look at the details, we can see that this argument diminishes important aspects of scientific practice. So, for example, Feferman wouldn't accept understanding the continuum in theoretical terms, but even if science can be carried out without that assumption, it would be really hard to teach science, to teach mathematics, to divulgate science, to understand it without this association. Okay, and in the end, there is a problem with a problem related to internal applicability. So, if we don't only consider as relevant like just mathematical applications to science, but also internal questions that appear when working in previously defined mathematical structures, then the set of theories that we could consider like legitimized through applicability would increase a lot. And an example is the proof of Fermat's last theorem that requires really high abstract set theoretical tools, which in the best case scenario can be carried out in 6th order arithmetic. So if you don't accept that frameworks, that tools, then you are like forced to reject the proof of this proof, and that's a little bit problematic. Okay. Okay, I am going to end it here. So I propose like to try to develop a framework for understanding legitimacy in mathematics, and this framework would be developed this way. So you kind of start with a recursive sequence of classes of mathematical structures. In the first level, I am sorry because I am like going too fast, but maybe if you can ask me later or whatever, I can tell you in more detail. In the first level, S0, we would have like the scientifically applicable structures. And later on, in higher levels of the hierarchy, we could have structures that are defined in terms of the previous one with one of the three following features. So if you have a structure that solves problems to previously defined relevant problems inside a previously defined structure, for example, in S0 we could find the basic conception of the natural numbers. And if we can find a structure that helps us solve problems in this structure, then we could admit it in the S1 level of the hierarchy, and so on. Okay, so if we could find so if we could put the structures that make us able to define CH in terms of this hierarchy, then probably we could answer some questions about this problem. And this is like the following step that I would want to follow in my research. Okay, so I can leave it here, and if you want to ask me anything, so feel free to ask. I am sorry for.
Thank you very much.
Okay.
So, do you have questions, comments?
Okay, whatever.
Yeah, can you
Yes.
explain
This in more detail.
Yes.
Oh yes, sir. Okay. So
Is it intersection or union?
I think it is a union, but I got messed with latex, so it should be a union. Okay, yes. Okay, yes, the idea is. Let's see. Okay, for me, the most paradigmatic example of a mathematical structure that was considered non-legitimized, but later came to be considered legitimized, is the complex numbers. Okay, so the question is why complex numbers ended up being like an accepted structure by mathematicians, while before they were like just like these things do not exist, they are unclear, why do you talk about them? So maybe all what Feferman has said about continuum hypothesis could have been said in those times about complex numbers. But in the end, they became accepted because of these reasons. First, because there was like a theoretical apparatus already developed with probably natural numbers, a really simple conception of the continuum, of the real plane, of calculus, etc. And they found that complex numbers were a tool for making. It was a tool for solving internal problems in those previously defined frameworks. So complex numbers brought solving problem because it gave a lot of solutions to previously defined problems, obviously algebra, etc. It gave also explanatory unification. For example, we all in mathematics we all see that this series can be developed by a geometrical. Okay, this is a mathematical example. This function can be developed by a geometrical series, but while this one also, I think it's like that. I think it's like that. Okay, and both of them are valid only if x is smaller than 1. Okay, but this one, we see easily why that happens, because this function has a singularity in x equal 1, while this one has no singularity in the real line. But this function does have a singularity in the complex plane, and it has a singularity in x while I equals I. So you cannot define a radius around the origin in the complex plane for this function where it doesn't have a singularity. So it provides also explanatory unification, like disparate phenomena become integrated when we consider this structure. And also it created new areas of inquiry inside the previous structure that people had not thought before. So for this reason, in case, for example, natural numbers or a pre-theoretical real line that I will note as real Euclidean line, if this were in S0, so probably a simple conception of the complex numbers would be in S1. So we could try to understand where these different structures fit in this hierarchy. and it would like shed a little bit of light on this problem. Maybe we could say, okay, Feferman, maybe you are going too far in saying that CH is an undefinite problem, but maybe you are right in saying that it is like a little bit more abstract, it is a little bit more higher in the hierarchy, and the structures needed to define them than in other more simple cases that maybe we should work more with because they are going to give us more useful tools in present. Okay. Yeah, sure.
I've been stuck, sorry, I missed the last part.
Yeah, sorry, because I didn't compute a lot, very well time, so in the end I had to run a little bit.
The problem was, that comes from the importance, seemed to me, you gave to this small dash.
Sorry, what?
The small dash for...
Well, yes.
The ideal picture of the world versus the picture of the ideal world. So,
yeah.
So, first question, I mean, do you think it's just typographical inconsistency from Solomon and
Feferman? Well,
like writing these conditions with a dash or not in the next
yeah.
paragraph, but
He was old when he wrote that.
Concept. No, old, I mean, it's just, in fact, because I was thinking, is that really?
Well, I have thought that, so I want to...
What is the importance? I mean,
okay.
You seem to be clear that they are different things.
Yeah.
And then they are different things, I was just thinking about
Yeah,
it.
yeah.
So suppose we have the best theory of the world.
Okay.
Society that is of course communism, right? Not for Arabs, but suppose we have communism.
Okay, communism.
You understand communism as a picture of an ideal world.
Okay.
The communist paradise, right? but, so you can understand communism as that, or something like that.
Okay.
So yeah, a picture of the ideal world. Or you can understand of a theory of the world, but an ideal picture of our world, right? Taking away the bad things in the. So you are also building a world. I mean, so at the end of the day,
yeah,
it is the same thing. It's communism.
Okay. Okay.
So you can look one way, you can look the other. You can put the dash here. You can put the there. There is no. Not entirely clear. There is a slight ambiguity, But this time now, for me, it's clear enough. I mean, they're the same thing, more or less. Now, for you, it seemed to me it is not. I mean, it's clear they are different.
Okay.
Right? And so I'm ready to accept your explanation why it's so important that difference and
why the hyphen is that important.
This is 3, and later on, in wherever there were these 2 paragraphs.
Okay.
Say, hey,
okay. Well, I don't know where to start. First, well, I don't think I thought, well, maybe this is a typo, putting the hyphen here or not. I don't think so. First, because Feferman has been a logician, and logicians tend to be really precise on whenever they put everything. So something such a detailed point, he should not be how can I say? He shouldn't be let that happen without a little bit of. I hope so. And also, it's not only in that moment. He also has been given like a lot of importance to physics and to applicability of mathematics in a lot of moments around his career. So he has worried for the idea that mathematical entities are applicable in the real world. For example, in this text in 1997, he says, "I have come to conjecture that all scientifically applicable mathematics can be formalized in system reducible to piano arithmetic." So really simple system. So he has tried to work a lot on that stuff. Okay, then about communism. Okay.
Good physics that gives you like an ideal picture of reality,
okay.
or it is given a picture of an idea.
But it's mathematics. I mean, Feferman is, I mean, mathematics, sorry.
Yeah, well, okay, I have, well, okay, yeah, so.
I have a pinky in this one. So, very stupid comment, but ideal word cannot have a hyphen in English, I would say. So, a word picture can have a hyphen, but you cannot link with a hyphen like grammatically referential adjective and a, no? So, it should be a typo.
Maybe.
I'm not very sure about what I'm saying. I
Well,
know for sure
in
that in math
mathematics,
you cannot do that.
but in mathematics, in philosophy of mathematics, if you're a Platonist, you think that all structures are about an ideal world. But Feferman is not. So it might be an ideal picture of the world. So that's different. I mean, it's not communism. It's like a Platonic world, or as the 10th thesis that you say is kind of this conventionalist, close to intuitionism kind of view, like
yes,
sort of mental construction, social construction about the world, not about the ideal world, not about Platonistic world. Communism is not a good analogy in that sense.
No, we're talking about, okay, the physics. I mean, we put this example of physics. I mean, and
yeah.
it was not, I tried to avoid using the dash, but that's right in the dash. I mean, for me, it's not clear, given the meaning of ideal and the word and of picture, that putting the dash here or the other one makes a difference.
Well,
so maybe, and you mentioned, we mathematicians, you know, we don't
well,
write everything.
Well, yes.
He's a mathematician, so, you know,
well,
assumes that there is no.
No, but we write. We don't write everything when it is clear from context, but I don't think this is clear from context. But yeah, yes.
One thing is to say you have the real world, and then from that you're building this kind of through abstraction or whatever abstract ideal structures. The other word is you have the ideal world, and now you're trying to write a picture of that.
Yes.
That's the difference.
And exactly.
The fact that it's not incompatible doesn't mean it's something different.
Exactly. It can be an ideal world picture, can be an ideal world picture.
Might be both.
Yeah.
You might get some picture.
Yes.
But he uses both. So what does it mean? That's my question.
Yeah. So.
Why is relevant the dash?
I mean,
What does it show?
for example, maybe I am going to present a mental experiment, a little mental experiment. Imagine that we were like calculators. We could be able to add numbers without any effort. Probably mathematics would have never existed because we wouldn't, well, maybe not, I'm like pointing at, but imagine that we're only interested in mathematics for computing. We were in the Babylonian time. In that case, probably mathematics wouldn't have existed. So in that case, we wouldn't need natural numbers to abstract operations and to abstract some ideas, because probably we wouldn't need it in that case. So it seems that mathematics has, it's not in what mathematics says, because mathematics says 1 + 1 equals 2. That doesn't say a lot, but in why do we consider, and that was something I passed a little bit fast, I think it's here. I am in the other direction. Okay. Okay, so if you accept structuralism, if you accept that some structures do exist, I mean the main point of mathematics, the main statements that mathematics makes apart from pure logic is that some structures do exist, but which structures do exist seems to have a relation with how we live in the world, with how we understand things in the world. So for this reason, I think that there is a difference between that, an ideal world picture, it is a world picture in the end, so it has a relation, it helps us understand the world in which we live in a determined way. This is my interpretation.
And just to explain, no, I was thinking again about this word. The ideal world, ideal dash word exists like possible word semantics. You know, when you have three things, you have to disambiguate sometimes.
Yes, like disambiguate a little bit, yeah.
Unifying
I'm not really sure about
possible word semantics is the possible
Yes.
dash,
So-
possible dash.
So maybe,
I'm not sure, but
yeah,
in some languages you cannot do that with referential adjectives, and I thought it was the case of English.
Of
but
English.
it came from-
yeah, but maybe
and
it
you
is,
can do it too.
it could be a grammatical mistake, but he like makes it so that it is clear what he is saying in that case.
I would say it's a typo. Yeah, I don't know. Eros has another question.
Sure, yeah,
Let me say first that I really like your talk,
okay, thank you.
and if you allow me to ask you a very basic, stupid, ignorant question,
For sure that is not.
from the one coming from mathematics, and
Okay,
but the one coming from linguistics,
yeah,
and when you're saying, for instance, what basic concept of structure, etc., I could not think about sociostructuralism,
okay,
which so much go with holism against atomism.
okay,
And you mentioned wine. And so I think that from a purely methodological viewpoint of philosophy, very abstract, very whatever, looking from very above without seeing all the detail, it seems to me like Feferman, in the picture you presented, from a methodological viewpoint, even from a cognitive viewpoint, linguistics, etc., it go hand in hand with kind of or Saussurean structuralism to some extent in linguistics.
okay,
And you got only structures, and you cannot have the atoms. And it's only the structure, it's only by contrast the component of the structure you build and you got
yeah, like the
kind
conceptions
of
or,
holistic, and so you were to some extent committed to holism and not to
Okay.
atomism.
yeah,
There was a big debate in philosophy,
Well,
but it was
it-
a very naive question from a
Well,
very ignorant guy.
in my case, I am a little bit naive on Saussure structuralism because I don't know it that much, so I don't know if I can answer you that much. But well, I think it could have a relation. So, but it's true that Feferman does not defend structuralism, but he takes it for granted. Probably he assumes that mathematics is given in form of structures, and it's quite natural idea nowadays. When Christian exposed in his talk, he talked about the completeness theorem in mathematics, and the completeness theorem says more or less that in case you have a consistent theory, you can have a structure. You will have a structure modeling them. So it's like a connection between logic and semantics, and syntax and semantics. And the point I made there was that from this theorem you kind of get a little bit that structure should be like, just formulating that theorem implies accepting like structures as the basic notion of mathematics, because if you understand structures in terms of axioms, then you would need axioms of set theory to be defined in terms of syntax, and then you would get kind of a small circularity. So it's like really natural to assume that mathematics works in terms of structures, and it's like coherent with mathematical practice, because in the end mathematics work like that. They work with natural numbers, with groups, with topologies, with all that stuff. So it's like something that is almost a religion in the end, because we have worked with that for a lot of time. Okay?
Plus, one of the criticisms of Saussure,
Yeah.
who did a great Feferman, for sure, was going before, one of the criticisms he faced was you risk to fall into circularity
Yeah.
and how to get out.
Yeah.
So there are similarities.
Yes, there are probably are similarities.
To me, but
Well, I would.
it's a similarity which also break down from an epistemology of cognitive science viewpoint on the way we kind of frame whatever pre-theoretical, how to define it, to conceive the world to be
Yeah, well, I will have to.
philosophically important questions.
I agree, yes. We will have to inquire probably more on that, on social structuralism. Maybe I can get.
Yeah, so just two small questions. One, I think we've already discussed, but
Yeah.
at the beginning, there are three slightly different claims. You say Feferman claims. I mean, you describe Feferman's claims about the continuum hypothesis. First, kind of whether it is meaningless, and another
Okay.
whether it is vague, and another
Yes.
whether it is not definite.
Okay.
And it seems like, okay, but these are different things. One thing is to be vague, another thing is to be meaningless.
Yes.
And if it's not meaningful, all right, that seems like a much stronger
Yeah.
claim, right? So
Okay. Yes. Well, in reality, so I have put meaningful with some people, so I have left it like general. But Feferman says that CAs can be or indefinite or intrinsically vague, but Feferman does not use the word
so he's
meaningless.
careful with that, yeah.
Yes, he's careful with that. Well, he uses it in a footnote, indirectly. That's the only word. So, there is a moment where he more or less points out at the idea that maybe it is meaningless.
Because for a mathematical statement,
Yeah, it's kind of.
that if it's not definite,
If it's not definite and it's vague, it's meaningless. Yeah, I think it probably is, but Feferman is cautious and he leaves a lot of things like so that we can deduce it but not explicit.
Sorry, can I add? And at some point you say overly concise.
Yes.
And that was whose words? Because
No, overly concise is my word. I say that about Feferman's thesis of conceptual structuralism.
it's being condensed. Because
Well, maybe.
concise seems to be a good thing in mathematics.
Well.
Unless, I don't know, I'm not really discussing the word
Okay.
concise,
Well. Well, yes. I don't know where. Yeah, here is so concise.
It's not about the continuum hypothesis, but about the way
About-
in which Feferman presents the
About conceptual structuralism, about the thesis of conceptual. I meant that they are like a little bit narrow, so they don't explain in detail everything that we should want to. Distance is it.
I think it has maybe two.
Maybe yes, I could obscure something like that. I would want to say.
No, Inigo.
Inigo or Javi, yes.
Oh yeah, lots of questions.
Yeah, yeah, there are questions.
Yeah, so I have a very basic clarificatory question. So,
Okay.
In this kind of discussions on philosophy of mathematics and so on, is legitimacy and existence more or less understood in the same way?
Mm-hmm.
And just in relation to that, so when people here are presenting different theories of mathematical legitimacy, I was wondering whether there is a kind of a broad agreement on which are the kind of paradigmatic mathematical entities that everyone agrees that wants theory to account for, or even there is no kind of agreement in that regard. So you have both disagreement in the side of defining a theory and which are the entities
Accepted.
I mean, it's just because
Yeah.
there are, I guess, many cases where you have these sort of problems where there is no agreement in any other sides.
Well, I'm sorry to say that probably. Oh, sorry. I mean, probably like in any area of philosophy, there is almost disagreement up to everything. So. Where is my favorite slide? It took a lot of time to do it in LaTeX. Okay, so for example, there are finitists. So there are people that only accept finite sets, and that's it. So maybe apart from that, it is there is agreement, but everybody agrees that there exist like numbers like 0, 1, etc. Not everybody accepts that there is a set containing all the natural numbers. So there we can find a strong point of disagreement, and there is also intuitionists that say that you cannot say even 0 exists or 0 doesn't exist. You cannot say that, according to Brouwer, no? The Brouwer.
There are nominalists that will say not even nothing exists.
Yeah, so there are nominalists who say so.
But you can say that. The other thing is that it's not a tautology, right?
Well, you can say it, but it's not true.
So the thing about legitimacy and existence.
Yes, and then legitimacy. Well, legitimacy is a little bit more philosophical term, while existence is a more formal term. In any theory of logic, you can ask about existence. For example, there are there are pluralists of set theory. There are people who say that in some set theoretical universes you can have some sets that exist and others that don't exist, while in other universes it would be different. So in one universe CH would be true, and in another universe CH would be false. But for those people, CH is a legitimate question, and all the universes are legitimized. So I think that legitimized is like a little bit more philosophical term, while existence is a little bit more formal term in this context, I think. So not necessarily, I would say that if an entity is legitimized, mathematical, it exists. I would say that. But I don't think that everybody would agree on that statement. Okay? Okay.
Yeah, just one question. Yeah, we have a question.
Yeah.
Thank you for the talk. I don't know much about these things, but I got stuck with an idea of the structure of the talk more broadly.
Yeah.
So you began explaining us
Uy, tienes que... Ah, sí, cógelo, claro.
Continuum Hypothesis.
Yes.
No, which is the conjecture that there is
Bueno, está
no
luego.
set between
Exactly.
the first set and the rest.
Exactly. Natural, real, a third set. Okay.
And you said that Gödels
And Cohen, yes.
proved
Yeah.
that you cannot either say
Yes.
that you cannot, I don't know how to say it in English.
You cannot prove it or refute it.
You cannot prove it and refute it. But they prove that you cannot
Exactly, yes.
do that. That's one part of the talk.
Yeah.
But then it seems that there is an issue with people that I don't get that you cannot prove because it is meaningless, it is not clear, or you cannot prove because you cannot prove it. So if they prove that you cannot do that, it must mean that it's meaningful somehow.
Okay.
So I don't,
Yes.
maybe I don't know if I am missing something.
No. It's a good question, but I didn't have maybe time to put it in precise terms, but it's a good question. So, I mean, so you can... I mean, the hypothesis could be written something like that. There is not a inner such that cardinal of n smaller than cardinal of a, smaller than cardinal of r. Okay, so it is clear that this is a statement, a definite statement in set theory or third order arithmetic or whatever. So nobody can doubt that because it would be absurd. But where Feferman doubts is that lie upon is the point that whether we can define an accepted and legitimate mathematical structure where this statement can be effectively decided. I guess that would be the exact meaning of the idea that it is an undefinite or an intrinsically vague statement. So you cannot. So it ends up being just a game of signs, but without a real meaning behind it, because to be a definitive statement in a legitimate mathematical structure would have to fill a little bit more conditions. So it would have to relate in some way to the world. It would have to be clear. It would have to connect to real life processes, etc. Okay, so it is clear as a logic statement, as a logic statement set theory, but it's not clear like in the semantic way. Okay, it's like a syntactical statement in that regard. A little bit like intuitionist. Intuitionism rejects that statements that seem like well written and that seem like we would well written in language, but do not connect to reality. That for intuition is intuition, so do not connect to reality endlessly. Okay.
Think of several questions in philosophy, like positivist or empiricist. They say, "Oh, that's a pseudo question." Question in ontology. We understand what the question says, but it's a pseudo question.
Yeah. Yeah.
Not
Yeah.
Pseudo questions.
Yes. Yeah.
They were saying ontological questions.
Yes.
They don't have meaning in that
Yeah.
sense. They're not really questions because they're not.
Yeah. Moral is.
But for
Yeah.
a philosopher, might be easier.
Yeah, and in fact, the proof of the undecidability of CH is formulated in really weak. So the proof is almost like done in terms of managing symbols. It's purely syntactical, and it can be carried through in really basic structures. So you could say that in the natural numbers, you could assign its natural number a symbol and do some stuff, and then the proof would get. But in the end, it's a proof in logic more than a proof in mathematics. The one of the undecidability of CH. So in the end, Koellner and Gödel's proof. It is, in fact, it is developed in finitary logic, or you use like just finite symbols and you develop finite proofs. Like following the idea of Hilbert's finitism. So it can be carried through in really weak systems. That proof of the undecidability of CH.
Even forcing?
I think even forcing, because you can do forcing with enumerable models, and in fact I think Koellner used the enumerable models, countable models. Yeah, I don't know if it's constructible in the end, but maybe yes. The proof of the consistency, I think, is constructible. Yes, I would have to check it in detail, but I think it's constructible.
Do we still have time? Or is there...
We have two questions. So
Okay. Well. Wait, but Javi didn't ask anything. Yeah.
Okay, so I just don't understand why someone would say that the continuum hypothesis is vague as a statement. I mean, it doesn't look vague to me. I think I can understand it.
Okay.
That's maybe that's vague about it. Maybe the predicators are supposing expressing the set of real numbers is vague, and maybe it goes that way. But anyway,
Yeah.
about it later. My question has to do with why does he think that the real numbers are unclear? Like, the sort of whatever conception of real numbers, or,
Okay.
or the structure itself, or whatever he's talking about. Why
Yeah.
does he think it's unclear? Because he says that so mathematical objects are mental conceptions coming from everyday activities, right? And he's
Yes.
counting, ordering, combining, space-time locating.
Yes.
And we could add also measuring, right?
Yeah.
Things that people did with sticks and things like that.
Yes.
Some time ago. And yeah, you could say you have a triangle with two sides of length 1, and then you have to sort of measure the remaining side of this equilateral triangle, right? And
Yeah.
you seem to be needing something more than rational numbers from it, right?
Okay.
Sure, you
Yes.
can approximate the length of the
Yes.
side with rational numbers, but it seems like the proper length of that side of the triangle, right, is a real number.
Yeah.
So it's an ordinary activity you do, right? You don't need too much, right? Just
Okay. Okay.
triangle in the floor. Same floor, right? And it seems to be due to the notion of real number. So my question is,
Yeah. Why?
what is it about them that makes them mysterious?
Okay, okay, it's a great question because this is one of the most one of the points Feferman makes that we can mostly criticize. But I am going to try to explain like Feferman's thought on that. So Feferman does not reject the Euclidean real line, which is like the basic structure where you can define all the classic geometry, but in the end, that's not as strong set theoretically as the real line that we use today. So there you can have lines, you can have concepts of parallelism, etc. But what Feferman does not like is that in order you depart from the natural number structure. Okay. Yes. Bye. A ver. Okay. Okay, so we depart from this. Better.
Much better.
My German professor bought a yellow pen for this, and you couldn't see anything, and it was a German word that I don't understand the word. But it's like concessive. It was like, well, I am going to do it in any case, so don't say anything. Well, okay, where were we? Okay, this is the natural number structure, and Feferman follows like is like a little bit leaning towards predicativism. So you cannot define any set in terms of parts that do only make sense referring to that set. That's the second point of predicativism. And in order to develop the power set of n, you end up just getting you get like all the subsets of n, but you cannot be precise on what this set refers to unless you have already thought on this set. That's the idea. So predicativists reject like doing these operations, so they have a lot of scruples on this set. So in the end, the real line is this. So he does not really like to use the real line. He has tried to use axiom systems that can be defined entirely through in terms of the natural number structure. And you can operate with natural numbers, you can approximate with natural numbers, you can create functions of reals, but using just predicative operations in terms of natural numbers, and he doesn't like to go a little bit further else. And he says, well, you can do science without this. And you can say, well, yes, but try to explain a first-year student of engineering how is the real life defined in terms of predicative formulas quantifying over the natural numbers. Obviously, nobody would study in engineering. So he's missing there, indeed, that point, he's missing a little bit of real scientific practice, in my view. Okay. Probably yes. In epistemology, how do you define?
It's kind of approach, but everything is given by
Yeah.
predicate, and whatever comes as a normal predicate has to be a verb, whatever, and it was sort of somewhat mirror the meaning of the whole.
Yeah.
Not from the predicate.
Yeah, so it's the idea that you cannot have circular definitions and you cannot, yeah, okay. So did that more or less answer your...
So the unclarity is in the construction.
Yes. So here you have a non-predicative construction, yes, that's the point.
Cristian, ¿qué pasa?
Okay, maybe can we go to 10?
10? Thesis 10 or...
Yeah, this is 10.
Well, I don't have the pen, so I have to...
I mean, my question is just about...
Here.
This is very interesting. I think there is, I mean, that's a very personal view, but I could give some examples where there is a sort of Darwinistic preservation of statements which are true in the society of people that do mathematics.
Yeah.
Not at the things that are sort of easy to prove, but there are statements that are so hard to prove, that are thousands of pages long proof, where it's a community of people that try to understand what the proof says, and in the end you get a sort of statement. But obviously I'm talking about things like the classification of finite simple groups, like huge results in mathematics that are extremely hard to prove, where no human mind can comprehend the whole proof, because it's a accumulation of many things.
Yeah.
And in this case, the truth of this statement is sort of socially accepted. Some people don't actually. So some people say, no, I'm not using that. And it's not even about independence problem. It's really about sometimes things are...
Yeah, yes.
We reach a point where things are just too hard. Is that related to... You said that there was literature on this?
Yes, there is literature on trying to approach mathematics in a conventional, in a social way. So, for example, in Searle's theory of institutions, like an institution is created by a declaration. So I declare this. How I say, this ship is called Queen Mary, and then there is a fact that is created because of this declaration. And there is like the idea that mathematics could be dependent on standing or implicit declarations. So yes, that just people act in such a way that those objects exist. But it's because of that standing declaration that mathematical objects exist. They have tried to make that relation, and I will probably try to...
And it also depends on trends.
Yeah, of course.
If there are a lot of people in mathematics working on this subject, then even if it's hard, then it will become sort of accepted and reliable. And some obscure branch of math that sort of was left a bit alone for a few years, then in order to get back into the truth realm, people will have to rework a bit on it and make it
of course, yes.
fresh.
So in the end, it's an interesting point. So we shouldn't criticize it and leave it apart without reflecting a little bit more. So it's for me it's a valuable point. Yeah, that's for next talk. Yeah, in fact, next paper or the following paper is going to try to investigate deeply this point.
Very short, and I don't know, it's probably minor, but I had a problem with your use of the word mathematics because sometimes, maybe for giving the examples you put from the beginning,
Yeah.
I thought you were using like almost in a narrow way to include arithmetics.
Yeah.
Opposing it to set theory or logic or topology, geometry. You have mathematics versus that.
Okay.
And at some other points, you include everything under the mathematics and under the term mathematics, right? Formal logic is there, and there are many other things, maybe geometry, and I don't know. The thing is, am I right? And I would, as you said, it went without saying probably for many of you, but for me, I would have appreciated like more consistent use of these terms or using arithmetics.
Well,
and when you want to talk about all of them, or or giving me a first panoramic, all of these different ways of mathematics there over there, and the ones that you are the ones you are going to accept in this the purposes of this talk, right? Because we have many things. I have no idea. But category theory. Well, there was a student here that was talking about category theory. I thought it was mathematics, but maybe some people...
No, it should be considered mathematics.
Some people say it's not mathematics.
Well,
model theory,
yeah.
not mathematics. Then you have standard model theory, non-standard model theory. I mean, there are so many things that usually, we understand being arithmetic, but then...
Well,
it's I don't know.
Yeah.
It's very minor. Maybe you can consider that for audiences like ours.
Yes.
You have a lot of people.
Yeah, maybe I could be more precise on that.
What we
Yes.
understand by mathematics.
Yeah. Well, probably. So I mean, there is an ambiguity on that question in the sense of this talk, because one of the objectives of the talk is to try to understand up to which point we can say that something is mathematics. Probably I would say that we have to try maybe like include a numeric or a set of numbers to start to be thinking on mathematics, but this is like a weak requirement, because in a set of numbers you can do a lot of things. In particular, in finite numbers you can do almost anything on formal logic, because formal logic follows a finite set of rules, so it's interested in finite proofs following a finite set of rules. So for this reason I put formal logic here, because I want to emphasize that finitists include formal logic in their reasonings because of this feature of logic. But yeah, probably I would say that mathematics is what is developed in terms of this kind of structures, like finite groups or arithmetic, natural numbers, geometry, but you probably always need a numeric structure to be able to talk about mathematics, but almost anything can be put in terms of a numeric structure, so mathematics is huge. So, but well, yeah, I would consider maybe precising this a little bit in another talk. Okay.
Okay, do you want to add something? So maybe you can leave it here.
Okay. Okay. Thank you for being here.
From a philosophical viewpoint, maybe we should go back on finite science viewpoint. It's a big debate.